Okay, so please don't confuse with the link. Okay, am I actually confused with the other departmental student with this class? Okay, so that is why I think.
Okay, sir. No problem, sir.
Okay, so previous class actually we ended up by talking about the important tensile properties like the measurement of resilience, that is the elastic energy of a material. Okay, so in order to measure that, first we need to do the tensile test, and then we have to take the we have to measure the stress and strain up to the yield point, or better, we need to measure the proportional limit in order to get the accurate value. Okay, so then if we measure the area under the curve, then we will be able to understand the modulus of a resilience of a material. Okay. Now here the thing is, what is the importance of measuring the modulus of resilience, and why basically we use this particular concept. Okay, so as I said, the mechanical testing basically used to fulfill the purpose of basic two objectives, like for design as well as for manufacturing. So from the design perspective, this measurement of modulus of resilience is important. Okay, why? That is because, let's say you are designing a bridge, so obviously you don't allow that the bridge will deform due to overloading. Okay, such that some plastic deformations will happen, which is the permanent deformations will happen. Okay, so from the design perspective, you should not allow that. Okay, so from that perspective, you need to know the proportional limit of that particular material or component that you are using. Okay, and then after knowing that, you will be able to calculate the overall the load that the bridge will able to sustain. Okay, so similarly for designing a column, or for designing the concrete structure, the concretes are highly brittle. So from that perspective, it is highly recommended that you need to measure the modulus of resilience of the material. Now the problem,
if it is nearly rigid body, then craft should be close to stress axis.
No, nearly rigid body, not perfectly rigid body. Okay, nearly rigid body means material ta fail korbe elastic region er moddhe, elastic মানে ডিফরমেশনটা হবে ইলাস্টিক ডিফরমেশন, বাট মেটেরিয়ালটা ফেল করবে ইলাস্টিক রিজনের মধ্যেই. So that is why it is nearly rigid body, means some amount of elastic deformations will happen inside the material. Though if you relieve the load before fracture, then it will come to its original position. So that is why we are using the term nearly rigid body, not exactly rigid body. If it is exactly rigid body, then no straining will happen. Is that clear?
Oh, okay, sir.
Yes, sir.
Okay. Now the next one is incompressible material like water. Okay, though some gravitational force is required to flow the water, but it is not we will not assume it is as an external load. Okay, so that is why you will find that without giving any sort of load, external load, the water or the fluid will flow over the floor. Okay, so that is why if you just plot the stress strain curve for the liquid materials, or whose density is relatively low in that particular cases, you will find this sort of stress strain curve. Now non-linear elastic curve you will observe where Hooke's law will be applicable, covering a little region, but after a certain stress level, okay, you will find the curve will bend like this, or some any other curve you will also find. Okay, here I have just put one curve, but some other type of curve also you will find which is not exactly linear. Okay, but if you release the load, then it will again come to its original position. But of course, here also you have to think it. You have to think in mind that the material should not goes beyond the yield stress of that particular material. So in that particular cases, you will find this type of non-linear elastic material, okay, such as rubber, elastomer. Okay, in case of metals, we generally see the nearly, the elastic curve which is nearly linear, okay, or exactly linear curve we'll see. But in case of rubber or elastomer, though the materials will if you apply the load and then material will deform elastically, but the curve may not be exactly linear. Okay, now after gone through this sort of different type of flow curve for different material, let's come that if you pick a single like steel material, then depending on the different parameters, okay, how the flow curve will vary. Okay, so I'm just going through the nature of a different flow curve or the stress strain curve, okay, for different material as well as for same materials, how they will behave depending on the different parameters or influencing parameters. Like here in this particular graph, you can see that I've used I have shown the different stress strain curve. Here, don't look into the elastic modulus of a material. It is for steel material, it is nearly equal, which is 200 to 210 GPa. But for the representation, I have just put it here just like this. Okay, so please ignore the elastic modulus part here. Okay, so here you can see that if you use the pure iron samples, okay, tensile specimen, if you use during tensile test, then you will find that yield stress of that particular material will be low, whereas the ductility will be relatively high. Okay, but if you are incorporating some other alloying elements like manganese, silicon, aluminium, copper, nickel, then you will find that your curve or your yield stress of a material will gradually increase. Okay, if you change the carbon percentage of a material of that particular material iron, you will also find the strength will increase as well as the ductility will compromise. Okay, so that means the stress as well as the strain of a material will also depend on the compositions of a material. Though you are using same materials, okay, but depending on the compositions, you can vary the stress and strength level. So that is why you will find that in marine engineering or in marine purpose or in war-like situations where the tank and the armored steels are basically developed actually by designing the compositions of a material. Okay, because of course for that particular cases we need to have the material which must experience the high strength and high toughness. Okay, so in that sense we need to design the material in such a way we can achieve or we can prevent the bullet or we can prevent the coming the hazardous things, okay, which can take the life of human life, which can take the human life. Okay, so in that sense we need to design. So similarly for breach purpose, we need to design a material which can which can absorb a moderate kind of load as well as which the toughness would be relatively high. So as well as we need to think of the cost of a material. Okay, so that is why the different type of material actually we need to develop or we generally develop in engineering and technology sector. Now in the previous curve I shown the toughness. Okay, but the thing is whenever we talk about the toughness, so it is not that we always want the high toughness of a material. তাতে আমার স্ট্রেংথ যাই হোক না কেন আমরা so we should not think like that. Okay, rather if we think that we want high strength as well as we want high toughness, so how we can improve the material property, okay, in that way. Okay, so always we need to think that such that that particular material will cover, or will fulfill the purpose in different sectors. Okay, so that is why today's research are going on development of the mechanical performance or the improvement of mechanical performance of a material. Okay, whether it is steel, whether it is non-ferrous materials, or whether it is the light metal alloys, something like that. Now we can also think that if you take a mild steel, here I'm taking this particular material. Okay, now even though you are taking a material having a particular compositions of that particular material, and you are not allowing to change the compositions, rather you can change the microscopic parameter of that particular material. Microscopic parameter means like microstructure you can change. So have you gone through the different microstructural constituents that may present inside the material? Do you know about these things?
Yes, sir. Actually, we have our metallographic lab, and in that we have studied the microstructures.
So I think mechanical and civil departments students, they may know these things, but
but still it will be favorable for us if you kindly share.
Yes, for electronics instrument and for electrical department, they might not gone through this sort of things. Okay, so I think today I forgot to take the image of those things, but yeah, I can tell you that in macroscopic view I can tell you, like I think all of you have seen that during preparing or the road, some sort of things or what I should say. Yeah, for preparations of road there, I think you will find that pitch is used. Similarly, some rocks, okay, the fine rocks or different graded rocks, okay, depending on the size, they may also used. Okay, but sometimes you will find that those rocks are available, or you can visually see those things. Okay, but if you change the percentage of those rocks or percentage of the pitch content, so you will find the different strength level of that particular road. Okay, and similarly, if I give an examples of like cake, okay, for preparations of cake. Okay, so if you use different constituents for preparing the cake, and then if you cut the cake, and if you sliced it, then you will find the different macroscopic features lies on that particular cake surface. Okay, so if you want to measure the strength of that particular cake, you will find the different, depending on the different constituent. Okay, you will find the different strength level. Okay. As well as if you change the baking parameters, then also you will find the different strength level of that particular cake. So similarly, in case of material also, you will find that depending on the baking parameter or depending on the heat treatment parameter, which is quite equivalent to the baking parameter, for similar materials, you will also change the strength of a material. Okay. In the next class, actually, I will show you that for different material, how the microstructural constituent generally vary. But yeah, for giving the definition of what is microstructural constituent, what is phase, so I need to tell you that the phase is nothing but the physically separable but mechanically inseparable. Okay, and chemically it has different, means different phase constituent has different chemical compositions. So in that sense, I tell you that if you change the microstructural constituent or the phase constituent, you can change the mechanical properties of a material. So it would be better.
So like thermomechanically twisted bar, like normal bar, or if we twisted them, then reach a higher strength.
Yeah, but that would be that is different issues. Okay, I'll tell you these things. That is not the actual answer from the current perspective. That is not the correct answer, because why not? Because for that particular things that you are telling, you are changing the strain. Okay, you are changing the strain. How? Here you can see that for that particular carb. Okay, if you take if you unload a material from a particular point which is beyond the yield strength, let's say you have withdraw the load. Just 1 minute. You have withdrawn a load at this particular point. In other cases, you have withdrawn a load. So here I have shown 3 different points, right? So if you just withdraw a load at 3 different points, and if you take out the 3 samples, and if you just measure the hardness of this particular material, you will find that 3 different materials shows the 3 different hardness. Means in one cases, if you unload at higher strain level, you will find that that particular material will shows the higher hardness values. So why that will show that will have that actually happens, I will talk this things just a little bit later on. But the thing is, whatever mechanical working you are doing on the material, okay, so that actually leads to the increment of strength of that particular material. Okay, so that is why you will find that just by doing heat treatment, you have developed a material, okay, and then you just do the tensile stress tensile test. Then whatever curve you will find, if you do some amount of mechanical working like rolling, okay, let's say initially you have taken 100 cross 100 cross 50, okay, dimension split, okay, whereas 50 is the thickness of that particular material. And the second material you have taken, like just by rolling or just by reducing the thickness of the initial material, and let's say the thickness you have reduced, 10 mm thickness you have reduced, and the third one you have taken where the final thickness is like 20 mm. So that means the third material that you have used, that you are using, maximum amount of deformations you have given to that particular material. So if you just do the tensile test, you will find the third sample will show the higher strength values, whereas the ductility will reduce significantly. Okay. Or the reductions of the strain will happen in that particular cases, okay, as compared to the second one. And the second one strength will also obviously increase as compared to the first one, okay, but the strain will reduce as compared to the first one. So basically, if you just do some sort of mechanical working or the metal working, either by doing rolling, by doing forging, or by doing any other type of, like short pinning. So if you just do this sort of mechanical working, you are actually increasing the strength of the material, okay, sometimes sacrificing some amount of strain or ductility, okay. So that is a separate issue, Okay, but here I am talking about that if you just take a simple single material without doing any sort of mechanical working, just by changing the heat treatment schedule, okay, you can change the stress and strain curve. Okay, just like you're preparing a curry. Okay, same curry you are preparing. Okay, but you are just changing the masala. Okay, you will find that the taste will be different. So that sort of things can happen in case of tensile test also. Now, yeah, I think this part have I covered this part, like how you can determine the different true stress and strain component?
No, sir.
Yes, sir. Yes, sir.
I think I just told you these things verbally, but yeah, you can find these things in the book of Dieter. But yeah, just I am telling you these things, like if you want to measure the sorry, the true fracture stress, okay, then you can just follow this sort of equations where the PF is a fracture load and the AF is a fracture in the area, the fracture area. Similarly, the true fracture strain you can also calculate. But here, whenever you just do this sort of calculations, please keep in mind that whenever we just convert the engineering stress to true stress, so up to the UTS, the gauge length is important. Okay, because throughout the gauge length, the deformations will generally happens, and that is why just by knowing the engineering stress, you can directly convert the engineering stress to true stress as well as the true strain. But beyond that, beyond the UTS, UTS, beyond the ultimate tensile strain, you have to continuously measure the cross-sectional area of the reduced cross-sectional area. That means there the preferential deformation generally happen, and therefore the whole gauge length will not taking part of this elongations. Only the reduced part is taking part. Okay, so that is why you have to measure the area, cross-sectional area, continuously. Okay, or let's say for 5-second interval, and then only we will be able to calculate. We will be able to draw the true strain curve till the fracture. Okay, but if we are unable to measure, then we can use the sort of equations which basically gives us quite approximately accurate values. Okay, not exactly, but quite approximately the accurate values. Now, in general sense, if we have this sort of stress strain curve, we can regenerate this curve, okay, by following this sort of equations, the flow curve equation, that is sigma is equal to k epsilon to the power n. How we can get this equations? Like if you have the data, okay, discretized data, then if you just draw in considering by plotting the stress at the y-axis and the strain at the x-axis, then if you just derive some equations using Excel or Origin, then you will find this sort of equation, which is known as the simple power law equations. But of course, this is not the exact solution. If you without doing test, if you just follow these equations, you cannot regenerate the exact curve. Okay, but quite approximately, you can redraw this sort of curve without doing any kind of experiment. Like for here, what are the variable presence? Like sigma is the variable and the epsilon is the variable. Okay, so just by changing the strain, you can easily calculate the stress values. But before that, you have to know the term K, which is a constant, which is known as the strength coefficient of a material, as well as the N, which is known as the strain hardening exponent. Okay, strain hardening exponent. So please remember that this is the strain hardening exponent. Now, what actually the strain hardening exponent tells us? It is basically depend on the the resistivity, that means during deformation the material will try to resist the deformation. Okay, so that particular things can be measured by measuring the strain hardening exponent. Okay, so how from the mechanical mathematical calculations we can also measure the strain hardening exponent. How? If we just take the log in both sides, then if you just plot the ln sigma versus ln epsilon, then whatever slopes we will find, okay, so that is nothing but the strain hardening exponent, and the interceptions intersect whatever we will get, that particular things is nothing but the strength coefficients of that particular material. But here you need to think, keep it in mind, I am talking about the strain hardening exponent. So you have to take the value till the YS to UTS, till the UTS value, because up to UTS, the hardening kind of things generally dominated. But after the UTS or after the ultimate tensile strain, what will happen? Though some amount of hardening will have happened, but the softening will predominate. Why softening? Because in that particular cases, the localized deformation is happening. So locally, the material will enormously soften. Okay, so the resistance part will be depreciated. Okay, but the softening or the decrement of the area will happen quite fast. So that is why the softening will dominate. Okay, so that is why whenever we try to measure this sort of hardening term, we can take the data from YS to UTS, means stress strain data in this particular range. Okay, in this particular range. In this particular range. Okay. Now, for different material, I will show you that how these things generally varies for different material. So, but then I will discuss about this particular curve. Okay. So here is an example, like for aluminium to the stainless steel, you can find that the N and K values will vary. Okay. You can find the K just I have said by measuring the interceptions, but here always you need to keep in mind the unit of this particular K values, which is equivalent to the unit of stress. Okay, or equal to the unit of stress, but N is unitless. But here you can just think that how basically the N varies, okay, for different materials. For metallic material, I would say that these things generally vary from 0.05 okay to 0.5. Okay, in the book sometime you will find that things generally vary from 0.1 to 0.5, but yeah, for high strength materials you will find that these things generally vary, or this strain hardening exponents lies below even 0.1. Okay, so please don't stick with that particular things, that yes, the N varies from 0.1 to 0.5. It cannot go beyond that particular range. Please don't stick with that particular range. Okay. Okay, now theoretically you will find that what will happen if the N is equals to 1? What will happen?
So it will follow the Hooke's law.
It will follow the Hooke's law. That means when the N equals to 1, means when for which type of material the strain hardening will be 1. I have showed the different graph, na? So flow graph or flow curve from perfectly elastic to perfectly plastic to perfectly rigid or nearly rigid body. So which type of material shows the strain hardening exponent which is equals to 1?
Perfectly elastic.
Yeah, perfectly elastic material. Okay. Now, when N is equal to, N would be equals to 0.
Perfectly plastic.
Are you sure?
Perfectly.
না ভুল বললি, ওটা ফুললি মানে রিজিট, পারফেক্টলি রিজিট হবে ওটা স্যার, পারফেক্টলি রিজিট স্যার।
Yeah, perfectly rigid body. Why? Can you please explain why?
So for perfectly rigid, there is no strain for applying any.
If you just put the equations or put the value of n, so here sigma would be equals to k.
K, yes sir.
Which is the strain coefficient. Okay, it
Yes sir,
dictates
that
the
will be
strain.
constant.
Yeah, that will be the constant value.
Yes sir.
So for that particular cases, okay. So for that particular cases, the stress will not be depend on the strain, right?
Yes
It
sir.
will not depend. The stress will not depend on strain. So whatever you have said, this perfectly rigid body. But if I just cover the area that is like something like this, okay, means if we change the strain, then also the stress will maintain. So can you say that this is that will be applicable for perfectly rigid body?
Sir, can you repeat the last sentence, sir?
I'm saying that the stress will not depend on the strain in that particular cases.
Yes sir.
So then can we say that it is applicable for perfectly rigid body? Means when n is equals to 0, that is for perfectly rigid body, or for perfectly rigid material, the n would be 0.
Sir, for a perfectly plastic body, the stress will be independent of strain. So why is it?
So whoever said the answer that is for perfectly plastic material, that is the most correct one. Perfectly rigid,
Yes, sir.
it is correct, partially correct, but it is not fully correct. Okay, but for perfectly plastic material, you can say that for perfectly plastic material, n will be equals to 0. Okay, rigid bodiর ক্ষেত্রেও ঠিক হবে, but perfectly plastic এর ক্ষেত্রেও ঠিক হবে, but perfectly plastic is the most accurate one. For rigid body, you have to say that the epsilon is equals to 0.
Yes sir. Yes sir.
তাই না?
Yes sir.
কারণ এই পার্টিকুলার ইকুয়েশনে তুমি যদি দেখো n equals to 0 মানে কার্ভটা yield stress রিচ করার পরে ওর স্ট্রেস ইনক্রিজ করছে না।
Yes
That
sir.
means the curve will follow, which is parallel to the x-axis. Okay, so which type of curve that kind of things will show? The perfectly plastic material. Okay, here if you just skip the elastic part, then you will find that the curve, whatever you will find, that is a perfectly perfectly plastic curve.
Yes sir. Yes sir.
Okay, now during during driving this strain hardening exponent, okay, we can come up with the another important term, which is the d sigma by d epsilon. Okay, now what actually it has also certain importance in analyzing the mechanical performance of a material. Okay, so I will talk about these things like this is nothing but the strain rate hardening, or the rate of strain hardening, or strain hardening rate, or sometimes we can call it as work hardening rate. Okay, so in the different book you will find this different terminology, but all are same. Okay, rate of strain hardening, rate of work hardening rate, okay, or strain hardening rate, but it has certain importance. What sort of importance? As you can see, If I give an example, first I will give an examples like if you just cross a road where no people are there or no disturbance is there, you just easily cross the road with a very short period of time, right? Similarly, in a material that you are using or you are testing, if no defects is there inside the material, okay, so initially if you just apply the load, first some defects will create. That means initially you can say that the straining will happen quite easily. I'm not talking about the rate of strain hardening, but the straining will happen quite easily initially, okay. But gradually, when defects will come into the picture or defects will generate inside the material, okay. Then that means when some disturbance will come into your road, so it will be difficult to cross the road quite easily. Okay, you have to pass. You have to first clear your road, then you can just easily cross the road. So similarly, same things here also happen. Okay. First, during deformations or during tensile straining, first defects will generate, and then more and more defects will come, okay, or more and more defects will generate inside the material. And during straining, which is known as the plastic deformations, okay, so plastic deformations will happen by following the slip mechanism or the cross slip mechanism. That means slipping will happen, okay, and then when the slipping will further continue, okay, then the material will elongate. So here when the lots of defect will come inside the material during slipping, those defects will also slip through a slip plane, okay. And that means the defects will glide through the slip plane. Then only the deformations will happen. Okay. Now, a lot of defects when come, then they will also interact and they will impede the movement of those defects. Okay. So that is why from YS to UTS, here you will find that gradually the load requirement for deformations will increase. That means as the defects or dislocations are interacting with each other and they are impeding the motions of those dislocations to assist the slip, okay, therefore you need to overcome those barriers. You have to apply the more and more amount of load, okay, till the UTS. That means, in other sense, from the rate of strain hardening means at which rate this resistance the materials are experiencing, okay. So that things can be measured by measuring the rate of strain hardening. That is d sigma by d epsilon. Okay. So that means in mathematically also you can calculate. Let's say you have the data, the stress versus strain data from YS to UTS, and initial stage you can the stress is sigma 1 and the strain is sigma 2. Let's say at time interval 5 seconds, you got the another stress and strain value, that is sigma 2 and epsilon 2. So similarly for t is equal to n, that means at tn times, you will get the n number of data, n number of stress data, n number of strain data. So each and every times you will be able to calculate the d sigma and d epsilon. Okay. Then if you just plot the d sigma by d epsilon with respect to stress or strain, you will get some curve. Okay. So how it will be look like you have just plot the d sigma by d epsilon with respect to strain. So you will find that the curve will vary like this. That means at initial stages, you will find the rate of strain hardening is very high, but gradually it will decrease. Okay. Why decrease? That means you are incorporating more and more disturbance into the road. Okay. But you want to cross the road very quickly. If you find that lot of disturbance in the road, you will find a lot of you have to give more and more amount of time to cross the road safely. Okay, so that perspective you can also apply here. So that is why you will find at initial stage rate of strain hardening is very high, but gradually this rate of strain hardening means the rate of increment of the barrier will decrease. Okay. Now here,
sir, this graph denotes the strain right from the elastic region.
No. Plastic region, not elastic region.
From the plastic region, it denotes.
Yeah. Plastic region. Because elastic region, what will happen? Elastic region, that will be straight line, more or less.
Yes, sir.
Yes, sir. Straight.
Constant. So the plastic regions, you will find this type of variation.
But sir, the strain, the rate of strain will be highest in the elastic region.
Yeah, you can say that. Rate of strain will be highest.
Okay, sir.
Okay, just think about the equation T sigma by T epsilon. Then you will find, because at the elastic region, you will find the change in stress is much more as compared to the change in strain.
But sir, why is it so? Like in the elastic region, why is it so? Because the dislocations start after the elastic region, right?
Yeah, you can say that dislocations start after the elastic region.
So, sir, why is it so that the rate of strain is highest in the elastic region?
The rate of straining is high, as I said, na ki jodi tumi eta ফাঁকা রাস্তা দিয়ে যাও তুমি কুইকলি পাস করে যাচ্ছ, হ্যাঁ? তো সিমিলারলি ডিফরমেশনের ক্ষেত্রেও এইটা তুমি করতে পারো, অ্যাপ্লাই করতে পারো, লাইক where the defect is minimum.
Yes, sir, I got it. Yes.
But please don't confuse that at the elastic region no defects are present inside the material. Okay, it is not that, because in that is actually theoretical perspective it is okay, but in practical sense no materials actually shows that means the absence of defect is very rare or even impossible.
Yes, sir.
Can you tell us that why, if no defects is there, then what will be the strength of the material, or what will be the strength of the material? You please do this exercise. যদি ধরো আমাদের কোনো মেটেরিয়ালে যদি কোনো ডিফেক্ট না থাকে, তাহলে মেটেরিয়ালের স্ট্রেংথ অ্যাকচুয়ালি কত হওয়া উচিত ছিল? Have you heard about the binding force or cohesive force?
Yes, sir.
Yes, sir.
So একটু ওটা স্টাডি করো, হ্যাঁ? That is related to the binding force and cohesive force.
Yes, sir.
Focus.
And then the next days you please give the answer.
Focus, sir.
Sir.
Okay, so now here just by drawing this sort of curve, as well as if we superimpose that particular curve with the true stress strain curve, you will find some intersection point. Okay, so that particular points you can think of that from this particular point the necking will start. Okay, how? If you just see these equations, okay, so you will find that this particular relation is also related with sigma and the strain. Okay, so let's say you are putting the value of n which is equals to 1. Okay, so at that particular cases, what would be the d sigma by d epsilon? You just shift the sigma and the strain side, so you will find some relations. Okay. Now, can you think of that when the n will be equals to 1? Or when the n will be equals to 0? If n is equals to 0, then what will happen in this particular equation? D sigma by d epsilon would be 0?
Yes, sir.
Okay. So you can also think of these two conditions. Okay, then I will talk about these things in the later on. That why we are considering the intersections of these two equations, okay, to evaluate the necking point. Okay, it is not that always means whenever you are doing the test, you are just noting down that where necking is happening. Okay, in which point the UTS of that particular material has reached. So it is not that. Sometimes we have to get the data, we have to have the data, we have to find the data, and then we have to analyze those data to find out the UTS. Sorry, what?
So one thing that at necking the stress is maximum means.
Yeah, stress is maximum.
So slope. So for maximization means d sigma by d epsilon means derivative that should be 0.
Yeah, that should be 0. D sigma by d epsilon would be 0. Okay, so if you, of course, here you need to think of the engineering stress strain curve, right? So don't confuse with true stress strain curve.
Yes,
okay?
yes.
So at that particular cases, if you follow engineering stress strain curve, you will follow that at UTS, the d sigma by d epsilon would be 0, or ds by de will be equals to 0. So from that particular sense, you also will to calculate. You can also put here this particular things is 0 or this particular things is 0. Then you can also calculate these things. Okay, but here I think you may confuse that is the true stress, true strain. Okay. In this calculation, okay, but in case of true stress, true strain, also it is possible. Okay, from the engineering sense, by just seeing the graphical representations, or by just measuring the slope, stress, engineering stress versus strain slope, you can think of that d sigma by d epsilon is equals to 0. At that particular condition, the necking will start. But if you just replicate these things in the true stress, true strain curve, you can just follow this sort of procedure. Means you have to measure the strain hardening rate curve, as well as if you just plot the true stress, true strain curve, then whatever will be the intersection point that dictates the necking point. How these things is happening, I will show in the next class by doing some sort of calculations. Okay, that means by doing the calculations considering the dp is equals to 0, means at what point the dp will be 0. Of course, at the instability point, the dp will be 0. So I will talk about these things in the next class. Okay,
sir.
আচ্ছা, আর একটা হচ্ছে যেটা তমজিৎকে বলেছিলাম, যদি অফলাইন ক্লাস হয়, শনিবারের ক্লাসটাকে ভাই একটু ম্যানেজ করতে হবে। হ্যাঁ
স্যার, ওইটা স্যার অনলাইন নিলেই ম্যাক্সিমাম স্টুডেন্টস বলছে স্যার, মানে সুবিধা।
আমার অনলাইন নিতে অসুবিধা নেই, কিন্তু সকলের একটু এগ্রিমেন্টটা করা উচিত, জানা উচিত।
আমি ওটা মানে গ্রুপে একবার জিজ্ঞেস করেছিলাম।
স্যার গ্রুপে স্যার সবাই আমরা স্যার অনলাইনের জন্যই স্যার করছি, কারণ এই মুহূর্তে অফলাইন পসিবল না স্যার। আর স্যার নেক্সট যে স্যাটারডে রয়েছে স্যার, ওখানে আমাদের স্যার গেট আছে। তো স্যার
ওই দিনে গেট আছে
স্যার, ওই দিনে ইঞ্জিনিয়ারিং সায়েন্স একটা পেপার আছে স্যার।
আচ্ছা আচ্ছা আচ্ছা,
সো ওই জন্য স্যার যদি আপনি মন্ডে ক্লাস নেন নেক্সট উইক।
ওকে ওকে, ঠিক আছে, যদি পারো। হ্যাঁ ঠিক আছে, কারণ তার আগে নিলে হয়তো তোমাদের চাপ হতে পারে। ঠিক আছে, পরে তাহলে আমাকে কিন্তু একটু টাইম দিও। হ্যাঁ, কারণ আমি হয়তো টাইম নিচ্ছি,
কথা বলে নেবো স্যার।
হ্যাঁ একটু বেশি টাইম নিচ্ছি, হয়তো কোর্স আমাকে তো শেষ করতে হবে না। পরে যদি টাইম রিকোয়ার্ড যদি দরকার হয় তো তোমাদের কাছে টাইম চেয়ে নেবো। হ্যাঁ
ওকে স্যার।
ওকে ঠিক আছে, চলো। হ্যাঁ,
থ্যাংক ইউ স্যার।
ওকে, বেস্ট অফ লাক ফর দ্য গেট এক্সাম।
Thank you, sir.
Okay.